Je vais redire ça. Okay. Okay, so we start the seminar. The speaker of today is Jean-Christophe Robinet. His topic, the topic of the webinar is transition to turbulence of laminar boundary layer due to synthetic jet actuation. And let me introduce Jean-Christophe briefly, and then I'll leave you the word. I'll leave you the stage. So in 1996, Jean-Christophe Robinet graduated from ISAE Super Aero in aerospace mechanical engineering, holding a research master's degree in fluid mechanics. In 1999, he defended his postdoctoral degree in fluid dynamics on linear stability of discontinuous flows with an application to shock waves at Tonnerre Toulouse under the supervision of Professor Grégoire Cassadet. In 2000, he then accepted a position as postdoctoral fellow at Marseille University under the supervision of Dr. Jean-Paul Dussault. on the study of the dynamics of compressible separated flows. In 2001, he became associate professor at Parametier Paris in the CNUMF lab directed by Professor Alain Lehrat, where he carried out work on modeling and numerical simulations of temporally self-sustaining turbulence, self-sustaining instabilities, with applications in shockwaves, shockwave boundary layer interactions, separated flows, and in presence of obstacles like roughness or cavities. In 2011, he became a full professor in the Dean Fluid lab. It's a pleasure to introduce Jean-Christophe Robinet. Please, Jean-Christophe, I leave you the stage.
Okay, thank you. Yes, thank you. Where is it here? I share my screen. Okay, you can see my slides. Okay. Today I will present you a work on transition to turbulence of laminar boundary layer due to the synthetic jet actuation. But first of all, I want to specify that this work is in collaboration with different guys, and particularly with Andrea Palombo, who carry out most of this work during this PhD thesis. And I collaborate also with Onofrio Semeraro, he's a chercheur at Lille CNRS, and also with Luigi De Luca, he's a professor at the University of Naples, Federico Due. For a certain application of engineering interest, boundary layer separation is a major problem which constrain and limit the design of many cases. And an example is the airplanes in landing and takeoff phases. In these phases, it's always interesting to have a boundary layer must remain attached as much as possible. And to do that and to maintain the boundary layer attached, it's necessary to reduce or ideally eliminate separation. And for do that, various control techniques could be used. And among us, we have mainly 4 categories. The first one is tangential blowing. The second one is wall suction. The third one is you use obstacle inside the flow, like vortex generator, roughness, etc. And the last one is excited forcing. You force the flow by many devices. Typically, in this talk, I we'll focus just on the control of the flow by force excitation. And in this category, we can have different type of jet forcing, continuous, pulsated, or synthetic. And the last one is very interesting because the synthetic jets are wider, slower, and have more momentum than similar continuous jets. Typically, an example is on the figure on the right from a comic in 2000. You can see, in fact, a wing with a high angle of attack. And this angle of attack, if you don't control the flow, is massively separated. And if we use array of small synthetic vortex, you can reattach the flow. And the main mechanism is you inject momentum close to the wall. And in this presentation, we focus on the synthetic jet, and more particularly the dynamic of the synthetic jet by itself. The main difference between pulsating and synthetic jet is the mass flow, which is 0 for the synthetic jet. And for the synthetic jet, the energy intake is in fact lower than the other facilities. Subsequently, the study will be limited in my talk to the synthetic jets. In fact, we can create a synthetic jet, in this case, an isolated synthetic jet, and it's produced by the interaction of the train of vortices formed by an alternating momentary ejection and suction of fluids across an orifice with zero net flux. And to do that, it's possible to use different technology to obtain the synthetic jet. Typically, electroacoustic devices. It's exactly these devices used by McCormick. For example, piezo-driven, he used typically by Glaser and Hamite in 2002. And also a plasma facilities is possible to use it to produce a synthetic jet. An example is Zhong use it to control the flow. In fact, in this study, you focus on the dynamic of an isolated synthetic jet in a cross flow. And in this study, it's restricted just on the analysis of the dynamic of the synthetic jet in strictly laminar boundary layer to understand the dynamic of the wake generated by the synthetic jet by itself. The design parameter for the synthetic jet in cross flow, you have mainly two: the momentum coefficient and the reduced frequency. For the reduced frequency, it's a ratio with the frequency of the jet, is the forcing frequency of the jet, and the reference frequency is the natural frequency of the uncontrolled flow. Typically, in this case, is the boundary layer. The excitation amplitude is commonly characterized by the momentum coefficient, and this coefficient permits to bring momentum to the boundary layer. For the reduced frequency, we can have different strategy for the synthetic jet design, mainly three. The first one is a quasi-steady approach where the reduced frequency is very, very small. The second one considered in this work is the interaction between the unstable mode of the flow and the forcing of the synthetic jet. And in this case, the reduced frequency is order 1, typically. For the last case is when you force with a high frequency in comparison to the reference frequency. And typically, it's a virtual aero shaping techniques. And this technique is used by Amite and Glaser in 2002, typically. For the computational model, I use a box enough larger to be independent to the dynamic of the boundary layer and the jet. Typically, I have 35 launch in streamwise direction, 10 in spanwise, and also 10 in normal direction. And the pipe is directly discretized and is chosen enough long to be independent of the initial condition within the computational domain, and such that this dependence of the resulting fluffing is the ratio H over D could be neglected because H is enough larger than D. The location of the synthetic jet is typically governed by the local Reynolds number of the boundary layer, and this boundary layer is fixed at the inlet by the displacement thickness. In fact, we fix a Blasius velocity profile at the inlet, and the displacement thickness of the uncontrolled flow at the jet position is assigned, and typically I use the Reynolds number with the displacement thickness to specify the jet position in this presentation. In fact, to solve the incompressible Navier-Stokes equation, I use NEC 5000. This code is an open source code developed by Fischer in the Argonne laboratory. This code uses a spectral element method. The formulation used here is a PNPN-2 and with Lagrange polynomial. In this study, the polynomial order is 9. And the grid is 30,000 hexahedral elements. The time integration is a third order backward difference, and I use 310-3 for the delta t. The simulation has been carried out in a parallel supercomputer, and I use more than 1,000 cores to compute this flow. It's important to specify the inlet jet conditions. For this study, I use Wormersley theory to describe the velocity profile at the inlet of the synthetic jet, the bottom part of the pipe, in fact. Typically, this velocity profile, we have different parameters, and the most important parameter is Wormersley number. Typically, Wormersley number, here the square of the Wormersley number is the transient, is the ratio between the transient inertial force and the viscous force. In this formulation, in this profile, I use a Bessel function, 0 order of the Bessel function to describe it, and this profile is validated by DNS. For the other boundary condition, I use a wall and lateral condition. The wall is It's the velocity component are 0. The lateral is periodic. At the inlet, I use blazes, and for the last part of my talk, synthetic free stream turbulence, and outlet, I use this relation. Typically, for synthetic jet, I have 6 parameters: free stream velocity, velocity for the jet, viscosity, kinematic viscosity, the diameter of the jet, the frequency of the jet, and the displacement thickness of the boundary layer at the position of the jet. We can construct different non-dimensional parameters to describe in the simple way this flow. Different ratio can be used. The ratio between the displacement thickness with the diameter of the jet, of the orifice. The position of the jet is governed by the value of the Reynolds number, governed by the displacement thickness at the position of the jet, the ratio of the different velocity. And we can link this ratio in uncompressible hypothesis. It's linked with the momentum coefficient. It's a root square of the momentum coefficient. We'll also use the Reynolds for the jet by itself, but is linked if we take into account the 2 first ratio described here, is linked directly to the Reynolds for the boundary layer. And finally, for the synthetic jet, it's necessary to define a Strual number, and this Strual number is defined by the frequency of the jet. We also use Stokes number, it's just the doubling of Wormley number, and I use the reduced frequency as described before. It's just the ratio for the frequency of the jet and the frequency for the reference. And this reference is the instability of the most unstable frequency of the boundary layer. If I describe the shape of the velocity of the inlet bottom part of the pipe, you can see the half evolution of this velocity profile for the 2 extreme case where we have the maximum of suction or the maximum of ejection. And for this case, the Wormley parameter is 16.1 typically. In this work, we compute many cases. I just present just a few of them, not all, it's too long. The 2 first cases is just a steady case. I don't present this case in this talk. And the other one, and S1 to R30, is a synthetic jet for different value of the parameter. Typically, S1 is my baseline. I presently just after more deeply. The case S2, 3, and 4, we modify just the reduced frequency. Is 0.5, 2, and 4 typically. The case 5, I use just a low value of Reynolds number for the boundary layer, typically 380. Case 6, it's a higher value, 660. The case 7, 8, and 9, it's similar to the baseline. The baseline is S1, and I just modify the forcing, the value of the the free stream turbulence, and I use 1%, 2%, and 4%. And finally, the case 10 and 11, it just I modify the value of the momentum coefficient, 2.5 10^-3 and 5.6 10^3 typically. The choice of the reference of the frequency is obtained by stability analysis, and the position of the jet is linked to this value. Typically, S1 is this cross. I don't know if you see correctly my mouse, and I use the Reynolds numbers 350 and the frequency where the TS wave is the most unstable. The other one, this cross is the K6. I just modify the Reynolds number and I use exactly the same radius frequency, F1, but the frequency of the most unstable mode is also modified. In this condition, I want to start to describe the dynamic by the baseline. The baseline is S1. The Reynolds number for the boundary layer is 350. The reduced frequency is 1. The frequency of the jet is exactly at the same frequency of the potentially most unstable frequency of the boundary layer, and I have no free stream turbulence for this case. On the beginning, I want to describe the flow inside the pipe by itself. The beginning of the pipe is here. I impose a Wormsley profile. And as you can see, the flow is progressively non-homogeneous and very dependent of the orifice of the pipe. And we have a big influence of boundary layer just upside. These two cases, it's the two extreme position, the ejection peak for the plot A and the suction peak for the plot B. And I plot the vertical velocity in my coordinate system is a longitudinal for the pipe. On the right, you can see in a dashed line the inlet boundary condition. It's typically Wormsley velocity profile. And on the solid lines, we can see the exit velocity profile, typically at the orifice of the jet. And is deeply modified by the evolution inside the pipe. Okay, now I want to describe the dynamic for this case. I plot the streamwise evolution of the vertical structure by isosurface of lambda 2. This, in the wake, we can look some hairpin evolution. On the near field, the jet creates rapidly hairpin evolutions. And after that, the hairpin grow rapidly and become to turbulence. As you can see, it's not exactly a turbulence in this case, but the flow, the complexity increase largely. Why you can create hairpin evolution in the wake? In fact, to create hairpin evolution, it's necessary to have 3 ingredients. The first one is a shear flow. It's the boundary layer. The second one is a contra-rotating vortex, is the blockage of the jet, which create a different contra-rotating vortex. And the last one is the oscillation, and this oscillation, it's necessary to have an oscillation, and this oscillation is generated by the jet because it's a synthetic jet. And in this condition, if you have these three kind of characteristics, shear flow, counter-rotating vortex, and oscillation, you can create hairpin vortex. And the dynamic of the hairpin vortex interact with the wall and generate streaks. These streaks evolve, create additional streaks, generally localized in the side part of the wake, and these two structures interact deeply and become turbulent. If I want to describe the convection velocity of these different structures, I use a correlation of the streamwise velocity fluctuation. As you can see on the figure A, it's just a contour map of the spatiotemporal correlation for the streamwise velocity at a particular position. And I pick up the maximum of the length in this correlation, and I can compute convective velocity, and this convective velocity is described on the figure B. As you can see, in fact, the convective velocity is initially constant. It's closer to 0.45 and sharply drop to the near field, and after increase when the transition is started. Typically, in the far stream, the flow is characterized by the interaction between adjacent vortices, the spreading of the wake, and the breakup in small structure. But if you look at these pictures, the flow is complex, but it's symmetric, in fact. The symmetry of the flow is not broken. You'll remember this point, and we'll talk about it in the second part of the talk. Typically, if I describe the dynamic of this synthetic jet, on the near field, you obtain a quasi-periodic behavior, and progressively this behavior becomes more complex and generates many harmonics. But for the high frequency, the flow is not exactly turbulent. It's very complex, but it's not exactly turbulent. And to be sure on this point, we can describe the time delay embedding, and the time delay embedding is a phase portrait where you compute the evolution of the velocity with a delay, and this delay is just 1 divided by 4 times of the main frequency. And in all of this plot, the phase portrait remains quasi-periodic, in fact. And the flow look like turbulent, but in fact no, because some symmetry cannot be broken, and we have many frequency, but it's also a quasi-periodic flow. If you detail more precisely the evolution of this flow, we can plot the velocity deviation. The velocity deviation is the difference between the instantaneous velocity and the Blazes velocity, and you see the evolution at different streamwise position of this wake, and you see mainly some different streaks in the near the wall, and these streaks in fact is responsible to the turbulence, and it's necessary to destabilize the streaks to become turbulent. In fact, the hairpin vortices is just an element, but is not at the origin of the transition. This plot is just an overview of velocity deviation, but it's a streamwise view of the velocity deviation, where you can see the evolution of different streaks, and the wake is spread progressively and create a lateral streaks on the wake. Typically, in the near field, the effect of the vortices is induced, an upwash of the fluid next to the symmetry plane, and downwash in external region. In downstream region, the vertical structures generated in the near field depart from the wall, while new vortices are created in the wall region, in fact. In the far field, the original hairpin vortices is far enough from the plate to organize themselves in an annular shape, while several small structures are paired within the boundary layer region. If we want to see more accurately the evolution, we can see the time average flow, and particularly the integral quantities, typically the displacement thickness and the momentum thickness, and the shape factor. And if we look at the evolution of the shape factor, you see at the beginning this value is compatible with Blazes boundary layer. With the presence of the jet, is decreased slightly, and after progressively in the wake, the shape factor decrease until the value of the turbulence one is around 1.5, but is not strictly speaking a turbulence, I said before. For the evolution of the skin friction, in this plot, we can see the streamwise distribution of the time average skin friction coefficient in the symmetry plane, and it's the black solid line. This evolution is in comparison with the classical Blazes in dashed line, and the turbulent one in dot dashed line. And typically, we have a weak evolution in the near field, and after typically after the streamwise position around 10, we can see a rapid evolution until a value closer to the turbulent value. For the skin friction, but in another plane, we can see exactly the modification of the skin friction by the presence of the contrarotative vortex and streaks. typically, if I plot the time average screen friction, but in the plane X Z plan, and I plot this streamwise evolution, and I compare with the laminar solution. In fact, in this point of view, the evolution of the skin friction in comparison to this one is more regular. And after, I only use this form of skin friction to describe the evolution of the wake. If I want to characterize the evolution of the streaks, it's interesting to plot this quantity. This quantity is the difference between the time average flow minus this quantity, but also average in transversal direction, integrated over the normal direction and the spanwise direction. And in this quantity, I can plot this quantity, just the second part of this quantity, the integral of the normal direction and the difference of these two quantities. These two quantities is u bar dxy. This quantity describe accurately the influence of the streaks on the boundary layer. As you can see, you see the evolution of the streaks downstream. These streaks evolve and spread in the spanwise direction. The intensity of the streaks characterized by this quantity evolve monotonically until a value of 0.5, typically 0.5 watt, 0.5 of the free stream velocity. In fact, it's very intense. It's for this reason, we have a strong interaction between the streaks and the vertical structure. And this interaction creates additional streaks, which create additional hairpin. And progressively, we become more complex and ideally turbulent. This plot finish the description of my baseline. Now I modify some parameter of the baseline. First of all, I want to understand the effect of the reduced frequency. Two cases are considered. The case 2, the frequency is just 0.5. And the case 3 is a double of the frequency for the baseline. The other parameter remains identical. The influence of the reduced frequency is very important, in fact, as you can see in these two plots, where we can see the streamwise evolution of the vertical structure in the wake. If you force by a lower frequency, typically the case 2, in fact, this case cannot create sufficient strong hairpin vortices. It cannot maintain, but in fact, this evolution decreases progressively, but it's enough stronger to generate the transition, but in a far stream. In fact, the transition is just delayed by the weakness of the generation of hairpin and the weakness of the generation of streaks. It's exactly the contrary for the case 3. This case 3 is very transitional. The streaks and the hairpin are very intense. We have a strong interaction between them, and rapidly we generate secondary hairpin, typically here, and and this hairpin become unstable to progressively have a complex behavior. In fact, from qualitative point of view, the topology of the flow are very similar. But more quantitatively point of view, it's not exactly the same. It's not exactly the case because the spreading rate of the vortices is higher than the reduced frequency increase. I recall at this frequency, the boundary layer is stable, modally stable, asymptotically stable. The TS wave is perfectly stable. Whereas the streamwise distance between the two consecutive hairpin is smaller. For the case 2, the creation of the train of hairpin vortices, which rapidly dissipate themselves during the motion. However, the streaks developed and destabilize around the streamwise position equal to 220, and generating a new cycle of vortex structure leading to the transition. Why the train of hairpin vortices which rapidly dissipate? In fact, because the recipes to generate hairpin is not obtained. I recall it's necessary to have three elements. Shear flow, okay, is not modified. Oscillation is modified by the frequency, and contra-rotating vortex is modified also by the frequency. And in fact, the two last one is not optimal to generate hairpin in this such case. It's exactly the inverse for the case 3. The case 3, the contra-rotative vortex is more intense, and the oscillation permit to generate hairpin easily. Typically, we can see this behavior if we look the streaks amplitude. Typically, the baseline is in dash here. The case for the lower frequency, the case 2, is in dot. It's the evolution of the amplitude of the hairpin increase less rapidly. The case 3 is in solid, is more intense than the baseline. And an important conclusion of this point is if we force by high frequency is interesting to generate an important dynamic inside the wave. But this case has a limit, because if we plot the streamwise location where the H factor fall below a certain value, typically 2, it's like a threshold to become turbulent. In fact, if I plot this this quantity as a function of reduced frequency, in fact, this quantity decrease until the reduced frequency 2. But after that, I have no evolution. And if I continue, typically f+4, the flow cannot transitional. We have a minimum. In fact, we have a minimum where the reduced frequency is more efficient to generate an important dynamic in the downstream of the pulsating jet. And typically, for example, the reduced frequency equal to 0.125, so case 13, and the case 4, where the reduced frequency is equal to 4, the transition is not observed in my domain. Perhaps it's necessary to increase the domain, but in my domain, the transition is not observed. All the dynamic is damped. For this value, both TA's wave frequency and the jet in cross flow one are not the optimal choice to maximize the control efficiency. It's necessary to find another mechanism. In fact, the instability of the natural instability of the boundary layer is not a good parameter to determine if the pulsating jet could be efficient or not in the point of view of the transition. The effect of the momentum coefficient. In fact, this momentum has a strong effect, as we can expected, because this coefficient is directly linked to the injection of the momentum. Typically, if we have a low momentum coefficient, typically the case 10 is like this, we cannot maintain the hairpin evolution. We create the hairpin, but progressively you decrease. It's similar for the case 11, but in fact, the hairpin is less intense. Why is less intense? Typically for the contra-rotative vortex. The contra-rotative vortex wrap around the synthetic jet is weaker than the baseline. And if we have three mechanisms, and one of us is deeply modified in this case in comparison to the baseline, and the contra-rotative vortex is weak. We cannot maintain the dynamic of the hairpin, and we have a threshold in momentum coefficient where it's possible to maintain it. Okay. We see exactly the same behavior if we look the evolution of the amplitude of the streaks. Typically, the lower pictures. The solid line is the baseline, is the case 1. The dash is the case 10, where the momentum coefficient is lower, and the case 11 is an intermediate case between 10 and 1. And typically we have a monotonic evolution on the streamwise direction, but also for the momentum parameter. In fact, if the momentum parameter is larger, the streaks evolution is more important. If the momentum is smaller, the streaks evolution could be almost null. And the streaks evolution and the contra-rotating vortex is linked by lift-off effect, is linked. We have a good measure to describe what's happened if we want to understand the creation and the evolution of different vertical structures in the wave. Typically, the evolution of the shape factor, the lower pictures here, you see an evolution. Typically, case 1 is solid line, so the more intense case, and we have also an intermediate case, and typically for the dashed line, we have a reverse evolution, in fact, because the shape factor increased slightly with the streamwise direction. For the intermediate case, the case 11, the dot line here, we have an intermediate behavior where the flow is destabilized, but the amplitude of the perturbation is not enough to create the transition, to generate the transition. This behavior is confined by the spectral analysis for the case 10. On the near field, we recover the frequency of the forcing. It's a vertical red line, and progressively the signal decrease in amplitude, become more complex by the generation of different harmonics, but decrease because the vertical structure can be maintained along of the wake. Now the jet streamwise position. In fact, this case is less interesting because the position of the jet, in fact, has a weak effect on the dynamic. Typically, the case 5, I use a very low value of Reynolds number for the boundary layer, and the case 6, it's a larger value than the baseline, the 660. The evolution is similar. The main difference is just in all cases we have the transition, but this transition is not very affected by the Reynolds number. In fact, this behavior is not a big surprise. Because the main effect is to generate a transition in the wake of synthetic jet is mainly governed by reduced frequency and the momentum coefficient. This behavior is confined by the evolution of the amplitude of the streaks. Is evolved quite similar for the 3 cases, the case 5, case 6, and the baseline case 1 is in black solid line. In fact, we have almost the same, and the hierarchy of this evolution is monotonic, sorry, with the value of the Reynolds number. The lower Reynolds number, we have the lower evolution. The baseline is in between, and for the larger one, the evolution is slightly more important. But in fact, the sensitivity of this parameter is not very important. The conclusion of this part is to reduce the boundary Reynolds number below its critical value, typically the case 5, does not modify the jet dynamic. The streak intensity almost remain unchanged for all considered Reynolds number, meaning that only the velocity ratio and the actuation frequency significantly affect the stream development. Okay. The last part of my talk is, if you remember my initial remark in the dynamic of the wake on my baseline, in fact, the dynamic increased in complexity, but the symmetry is never broken. In fact, we have many frequency, but the dynamic is always quasi-periodic. Now I force the flow by synthetic turbulence at the inlet, And to create the synthetic turbulence, I use the techniques developed by Jacob and Durbin in 2001. This technique has been developed by Alessandro Bucci in this thesis and implemented inside NEC 5000. And this technique, in fact, create a synthetic turbulence by the continuous mode of Sommerfeld square equation. Why is it interesting? Because all the continuous mode of Sommerfeld square equation are sinusoidal in free stream and tend to zero at the wall. It's a better basis than Fourier mode because y direction is homogeneous, and in this direction, the best choice to project in basis and to create a perturbation is the continuous mode in our Sommerfeld square mode. In fact, for each eigenvalue, it's a three-dimensional wave vector, and is associated by three wave number components, alpha, gamma, and beta, with the value of alpha is directly linked to the frequency, and it's typically the phase velocity comparable to the free stream velocity. The perturbation is decomposed in this basis where we have an amplitude, AN, and this amplitude is calibrated by an energy spectrum in Fourier space. And I use a von Karman energy spectrum to calibrate the amplitude of each mode. To do that, we divide the wave number space in 20 concentric spherical shells. The different value of the wave number component. I use a vertex dodecahedron to select the different value of alpha, beta, and gamma. These values are selected on the surface of each shell, and this shell is rotated, and we use a random phase shift is applied to increase the isotropy and to have no bias in the selection of the different wave number, and finally the different mode used to reconstruct the perturbation. Following the Brandt in 2004, we can introduce an integral wave length scale, and we can write the energy in spectral space in wave number with two parameters, the total turbulent kinetic energy and this integral length scale. The energy of each shell, typically the value of K, is determined by the equation just after, in where the square of the amplitude of each mode, this one, is linked to the von Karman energy spectrum in each range of wave number. And finally, if we do that at the inlet, we generate synthetic turbulence. This synthetic turbulence decrease in streamwise direction and force the flow. And if we look this kind of evolution, typically this plot is a plot from Zaki paper in 2010. The inlet of this flow is forced by free stream turbulence, construct like this, and the perturbation have a penetration depth, and this penetration depth generates receptivity of the boundary layer and creates a perturbation. And this perturbation, in this case, is a stress. And the intensity of the free stream turbulence is controlled by the level, the rate of the turbulence. Typically, when the rate of the turbulence is larger than 1%, the flow generates a stress. And see if it lower than 1%, generally we can observe a modal instability like TS wave and the classical transition from this point of view. If I use this forcing at the inlet, I describe 3 cases. The case 7, I force by 1%, 8, 2%, and 9, 4%. And the other parameter is exactly the parameter used for my baseline. The free stream turbulence does not really change the dynamic, but the far field behavior is slightly modified by the turbulent perturbation. And in this case, the symmetry breaking is obtained. The dynamic described previously, it's exactly the same. But now it's possible to have a real turbulent regime. To be sure on this point, it's we can compute a spectral analysis for different positions in streamwise direction. Typically, the case A, B, C, D, just the position is in central plane, and I evolve longitudinally on the wall, and I describe the phase portrait for this each position, and rapidly the phase portrait have an evolution not quasi-periodic. In fact, we have a chaotic movement, and is characteristic to the turbulence. And if we describe the evolution of the frequency spectra, in fact, in the range between 10⁻⁻1 and 1, we can see typical evolution with -5 divided by 3 power laws, characteristic to the turbulence. And this case, in comparison to the basic case, it's exactly the same. I just had a free stream turbulence, and this free stream turbulence act force the different scale, and particularly in spinewise direction, and mix this different scale, and we can have a turbulent behavior. In this case, the evolution of the skin friction, it's a time average skin friction coefficient on the XY plane for the case 9. We have the similar behavior than the previous one, than the case 1, but now the evolution of the skin friction is not symmetric. We have really broken all the symmetry inside the flow. And the spinewise average skin friction coefficient distribution is practically unaffected by the streamwise turbulence value. For each value that I use, 1%, 2%, or 4%, in fact, we obtain exactly the same evolution, but the transition process in near a wall region is not strongly affected by the free stream turbulence. Only the streaks are affected, and the vertical structure related to the streaks. One consequence of the free stream turbulence is skin friction is more homogeneous in streamwise direction. We mix the flow in comparison to the baseline, and this mixing is due to the turbulent dissipation. My conclusion for this talk, the downstream development of the vortices emitted through the orifice of the synthetic jet actuator into the laminar boundary layer depend mainly on the Tural number, the velocity ratio, but more weakly to the boundary Reynolds number. The effect of the reduced frequency, when the frequency is, this reduced frequency is small, the dynamics are driven by spatially amplified instabilities, while the dynamic linked to the hairpin are damped. For the intermediate value, typically between 1 and 3, the dynamic of the hairpin interact deeply with the dynamic of the streaks and generate the transition, because we generate secondary hairpin, we generate side streaks, etc., until the transition. The effect of the momentum coefficient. In fact, we have the threshold. If the momentum is too low, we have no transition. Just because the contra-rotating vortex is not enough stronger to generate hairpin and streaks. The efficiency of these coefficients depend on its ability to modify the momentum near the wall. Under this condition, the transition is driven by the interaction between the dynamic of the wake and the dynamic of the side streaks. The effect of the jet streamwise position, if we decrease 25% the actuator position, does not change fundamentally the dynamic. The transition is always driven by the interaction between the dynamic of the wake and the dynamic of the side streaks. The vortex structures are just elongated by the influence of the Reynolds. It's typically just a lift-off effect, and is not sufficient here to see a noticeable effect. In fact, if we want to observe more effect for the Reynolds number on the boundary layer, it's necessary to modify largely the position of the jet. And after, in fact, the dynamic is more complex because it's necessary to take into account the instability of the boundary layer upstream, because naturally the boundary layer is transitional if the position of the jet is largely downstream. The effect of the free stream turbulence. The main effect of the free stream turbulence is redistribution of energy to the small scale, resulting in a symmetry breaking and a complete transition to turbulence. And finally, this fundamental knowledge of the vortex structure will be useful then designing and interpreting the results for the future flow control studies, such as the separation control and skin friction drag reduction in boundary layer, involving synthetic jets emanating from the Citora orifices. Thank you. I'm finished. If you have some question, I'm happy to.
So thank you, Jean-Christophe, for the presentation. Then the stage is open for question. You can just activate your mic if you have a question, and in case someone else is speaking, you can write in the chat or just wait for Jean-Christophe to reply. Please go ahead. Any questions? Let's check.
Everything is clear, or
we cannot hear you. You need to activate your mic if you want to ask a question.
May I ask a question? I'm Kentaro Kato at KTH. I'm interested in the secondary structure or successive structures. What's the mechanism to developing these structures? Is there any instability? Or,
what kind of secondary structure? You speak about secondary hairpin or secondary streaks?
for each.
For each. In fact, for the hairpin, it's simple. In fact, if perhaps I can discuss with an example. Typically, in this case, in fact, by the lift-up effect, the leg of hairpin is stretched, and when the intensity of the vortex is enough important, we create a seed on each leg, and this seed of each leg interact. It's not clear. It's in instability like a crow instability, because you are contrarotative vortex. The two legs is very close, and we have the leg move slowly and interact and create a second half. And in fact, it's not really clearly described in the literature at this point, but it's necessary to have a threshold in intensity of the vortex. And in this condition, we can create a secondary arch of the hairpin, etc., etc. And when the hairpin is enough intense, in fact, on the center line of the hairpin, we have a shear layer, and in this location, we can generate inviscid Kelvin-Helmholtz instability, which destroy the hairpin. And at this time, you transition up. This is for the hairpin. For the streaks, this is a little bit different, because to create from the jet, we have like a horseshoe wrap around the jet if the momentum coefficient is enough larger. These two contrarotative vortex generate hairpin, and the hairpin, if the hairpin is enough stronger, we can have a secondary instability to the hairpin, and by the spreading of the wake, is it possible to create additional hairpin? The hairpin create additional streaks which generate additional hairpin, etc., etc. In fact, this behavior is correctly described in different cases, and particularly in the transition to the boundary layer, typically K and H transition. The late stage of transition is correctly described by a paper in 2007, if I remember, by Shen. We can have this description.
Thank you for your explanation and a nice talk.
So there is a question in the chat. I reported. So the question is, can you please comment on the effect of compressibility on this transition dynamics?
I really, it's probably the compressibility effect. If we have, if you are subsonic, is I think it's similar. You have no many modification. For supersonic flow, I don't know. Really, I don't know, because generally the compressibility is a damping effect in comparison to the incompressible dynamic. This damping effect is observed for the sorry for the moderate value of Mach number, typically less than 3, 2, 3. Probably the dynamic is very similar, but for the higher value of Mach, I don't know. I don't know, because the evolution of the streaks is not deeply affected, but the evolution of the hairpin, I don't know. Generally, it's more complex to generate hairpin in supersonic flow, but it's possible. But I really don't know. Probably the transition is delayed, but I really don't know if we can have a additional effect. Typically in boundary layer, you have a secondary mode. If the Mach number is larger than 4.5, I don't know if we can generate the different dynamic. For a moderate value of Mach number, typically it's just a damping effect.
Is there any other question?
Can I ask one?
Yes, of course.
Just behind the jet, the streaks, which is generated below the hairpin, did you try to look at the stability of these streaks? Because it seems to be very stable, because it stays for a long time, actually.
Yeah, I never tried to do that, but it's interesting. The only one case where you try to compute stability analysis is not for the jet, but for the roughness. It's a work with Alexandro Bucci. I think it's here. Yes, yeah, he's here. On this case, we can compute the stability of the strictly boundary layer. Yeah, and generally in the near field, it's very intense. It's highly unstable. If we compute the convective instability by typically two-dimensional local instability tools, we have many modes, especially unstable. But for the streaks, we never perform it in any case. I don't know. It's a good idea. In fact, it's interesting to compute the stability of the streaks. Typically, the secondary instability of the streaks. It's very interesting, particularly to explain the creation of the side streaks. It's very interesting, but we never do it at this moment.
Okay, thanks.
So other questions? Is there someone else who wants to ask a question?
Yes, maybe one. well, I'm not sure it's well. First of all, thank you very much for the talk, Jean-Christophe. Do you think that if I have understood correctly, I'm really not a specialist, but the problem is that you are not able to break the symmetry of the flow configuration you are studying, and have you considered? Do you think it could be a good idea to change the angle of injection of your actuator?
For the efficiency of the jet, yes, it's interesting. For the symmetry breaking, I think no. But for the efficiency, yes, because typically it's the angle is 90 degrees. It's normal to the wall. But the most efficient is probably tangential. But we never do this case. But typically, if we look the application of synthetic jets, sometimes the synthetic jet is with an angle, not tangential, not normal, in between. We have and if we have an angle, generally the efficiency of the jet is better for probably a simple reason. The objective of the jet is to inject momentum inside the boundary layer, and this momentum must be injected near the wall. If we have a normal jet, continuous or pulsating or synthetic, it's the same idea. In fact, the injection is not directly inject near the wall. It's necessary to have a migration of the perturbation in normal direction to be efficient. If we inject tangentially or with an angle, perhaps it's better. For the control, it's clear because many cases described in the literature choose an angle and not a normal direction. But in this case, we just want to describe the dynamic of the wake being behind the jet. For the control, it's necessary to consider this point of view. Yeah.
Yes, if I may, I was also I was thinking especially on the, let's say, the yaw angle.
Yeah.
Because you are thinking that yes, if we blow tangentially, it will be better. But I was thinking about changing the angle in the other direction, because in your case you are blowing in a direction which is already which is one of the symmetry of your problem in terms of geometry, and I was thinking that maybe changing the yaw angle of blowing could help to break the symmetry, but I'm not sure it's so relevant.
I really don't know. Perhaps, but in this case, it's necessary to have like a stochastic forcing to break the symmetry.
Okay.
Because if you compute in larger domain, in fact, the symmetry remains in far field. In fact, in all cases computed here, it's like this, and it's necessary, even if the behavior of the flow seems to be very complex. In fact, it's always symmetric. Yeah. And it's necessary to inject a small scale in spanwise direction to have energy transfer between the different scale and to start the real turbulence behavior, in fact.
Okay, thank you.
Okay. Are there any other questions?
Excuse me. Hi. Hello.
Yeah.
Thank you for the talk. it's like my question comes from what you just discussed with the previous question, and I know that we want to transfer the energy into the boundary layer to prevent it from from décoller. But what I mean is, how do? Okay, my question is, so a blowing jet that produces a symmetric effect would be bad, will be counterproductive, will not have the effect that we're wishing for. Is that right? Like, if I produce something, the symmetric case that you had in the baseline configuration is not a efficient jet. That's a question.
Not sure to understand your question.
What the thing is, sorry, the thing is, why are we talking about breaking the symmetry or not breaking the symmetry? I don't understand which one is the better case, or if it makes sense to.
For better case for what? For the control?
Yeah, for the control, for the application.
For me, the non-breaking symmetry is artificial. In real life, you broke the symmetry. In fact, numerically speaking,
it's pretty weird to have a symmetric result.
Yeah,
right?
yeah. I think yes. In fact, in real life, you always break the symmetry because you have noise defect. You broke the symmetry naturally. In computation, it's different because you can generate a clean simulation, and the clean simulation is a little bit artificial. It's necessary to have some noise, some residual turbulence, and this perturbation broke the symmetry at the end. In this case, it's a little bit artificial because if we have no turbulent forcing or no stochastic forcing, we cannot have the real transition. But
yeah, but precisely, like we're doing the extra step of adding an artificial component in order to have the development of the instabilities, right? But why don't we do the same to break the symmetry, since we know that the symmetry is not natural either?
Well, I don't know. For me, if we want to be realistic, it's at the end it's necessary to have a forcing, and the interesting point is the time average characteristics is very close to the turbulence one, but without symmetry breaking.
So it doesn't matter if you have symmetry or not symmetry.
After, clearly, this jet with this symmetric jet, if you want, clearly it's more coherent than the non-symmetric jet, and of course it's potentially more efficient, but it's not realistic.
It's not realistic. Yeah, yes. Yeah. Okay. Thank you.
Any other questions? Okay, this doesn't seem to be the case. So thank you, Jean-Christophe, once again.
Thank you for the invitation.
That was a great talk, and I remind all the participants that the talk will be uploaded on YouTube, on the YouTube channel of the lab, most likely before the